So chapter 8 is going to be a little bit funky, um, a little bit weird, to say the least. Chapter 8 is going to be about, well, we can calculate z-scores for single observations. But chapter 8, we're actually going to calculate z-scores for multiple observations taken at the same time. Multiple observations taken at the same time. Namely, we're going to talk about the mean. What does the average value look like in a sample or in a population? And can we compute z-scores and compute probabilities with that? So let me talk. Okay, so we can talk about this population. Let's say there's 4 elements in this population. So what we want to do, we want to compute the mean and standard deviation. And remember, this is a population mean and standard deviation. So we can do that. I'm going to use some Excel tools, but you can use calculator tools that you might have at handy. And we're going to get a mean of 5.25. And we're going to get a standard deviation of 2.165. For these 4 numbers. So we might just have to remember that in our mind, because we're going to have to scroll down here. So maybe I'll write it over here. And now let's look at what we can do with this. What we can do is we can take samples of size n equals 2. So what do I mean by that? Well, each one of these is going to be a sample here. So we think about it. You have the numbers 2, 5, 6, and 8. All the samples of size 2 you can take where you can use replacement, meaning you can use a number twice. You can take 2 twice, you can do 2 and 5, 2 and 6, 2 and 8. Then you can do 5 and 5, 5, 6, 5, 8, 6 and 6, 6 and 8, and then you can take 2 8s, assuming you are allowed to do replacement from the sample or in the sample. We'll talk about why we're going to care about that here in just a moment. So for this first sample of size 2, the average value is going to be 2. For this next sample of size 2, which has the numbers 2 and 5 in it, the average value is going to be 3.5. For this next sample with 2 and 6 in it, the average value is going to be 4. And so on. We can compute the average value all the way down the line. But then what we're going to do, we're going to do something kind of strange. I'm going to take the average value of all of these average values. I'm going to take the average value of 2, 3.5, 4, 5, 3.5, 5, 5.5, 6.5, and so on. The reason being is we're going to see that there's an interesting connection here. We're going to find an interesting connection. So let me enter all these values into my Excel spreadsheet. 2, 3.5, 4, 5, 3.5. Do something like this so I can even see it all. gonna have to rearrange the screen slightly. That's okay. Um, 5, 5.5, 6.5, 4, 5.5, 6, 7, 5, 6.5, 7, and 8. If we take the average value of this, it turns out, and it's pretty cool, it turns out the average of all these averages is 5.25. So the average sample average is the exact same as the original population average we started with. Now, if we take the standard deviation of all of these, if we take the standard deviation, so let me do that here in Excel. If we take that and we divide it by if we were to take the original population standard deviation, so here, we're going to get 1.5309. That's the standard deviation of all these values here. What we'll find, and we may not be able to make that connection ourselves without a little bit of help, if we took the population standard deviation of 2.165 and we divided by the square root of 2, where 2 was the sample size we took in each case, we're actually going to end up with the same thing, 1.5309. And you know, there might be a little rounding error in there. The whole point behind this song and dance, we're actually going to be using this formula here and this idea, this concept, in order to be able to construct probability distributions for samples. We're going to do all this so we can construct probability distributions for samples. Why are we doing all this? Well, if the population has a normal distribution, so we know that the population that we're pulling from, everything could fit along a normal bell curve. Well, then the sampling distribution will also be normal, meaning that whenever we look at the sample itself, the sample is also normal. If the population is not normal, we have a very important theorem in statistics called the central limit theorem. As we increase the sample size, as we take larger and larger samples, the sampling distribution approaches a normal distribution, whether or not we started from a normal or not. Now that's actually a huge revelation in statistics, one that we don't go into uber detail about here. But basically what we can do at the end of the day is we can make predictions and probability predictions about the sample average, X bar. And that doesn't sound horribly powerful, but it's going to allow us to ask questions like, okay, well, what if in a class of 25 people, if their test scores are normally distributed, each individual test score is normally distributed with a mean of 80 and a standard deviation of 4. I can also tell you the distribution of the average. What will the average test grade in that class look like? It turns out it will also be, or roughly will be, normally distributed, depending on whether the population was. So basically, we can use the standard normal table for anything as long as you have a large enough sample. That's going to be our major thing. How large a sample do we need? The number usually floats around 30. If you have at least 30 in your sample, then you can assume that the sample is going to be normally distributed as well. Again, it doesn't sound uber profound until we start to do some calculations and computations with all of that. But we can do that. So let's say you are sampling from a population. If your population is normal, if you know your population is normal, the sample size is irrelevant. Oh boy, irrelevant. Yeah, that's how you spell it. So if you're sampling from a normal distribution, your sample size is irrelevant. The sampling distribution will also be normal, no matter what. So you can sample and you can only have 5 things in your sample, and you can still say, oh, well, the sampling distribution is still normal. X bar, the mean, still follows a normal distribution itself, which is weird. All we've talked about before are single observations being normal and computing probabilities from just single individual observations. But now we're going to need to talk about probabilities involving a sample mean, the average value of a sample. Now, in the case where you have a sample of at least size 30, some textbooks will say 25, but 30 is usually the gold standard for this. If you have a sample size of at least 30, then it doesn't matter what population you're pulling from. It doesn't matter its distribution. We're going to assume that we're going to have a normal distribution for the sample. And again, this looks a little confusing right now, but we're going to see some examples, and it's going to help us. The average value, so the distribution of that sample mean is going to be normal with a mean that is the same as the population mean, mu. But the standard deviation, this is a different one. The standard deviation is going to be the standard deviation of the population divided by the square root of n, where n is the sample size. So that's going to be kind of our big revelation here. That's what it's all about. So let's look at an example. For women between the ages of 18 and 24, their systolic blood pressure, so if you go get your blood pressure done, you're going to see 2 numbers. Your systolic is the first one you'll see, I think, and then it's like diastolic or something. It's measured in millimeters, excuse me, of, I think this is mercury, because it's on a thing, it's on a thermometer looking thing that uses mercury, but it's not actually a thermometer. Let's not worry about the details. Your blood pressure for women age 18 to 24 is normally, or has an average value of 115 and a value of a standard deviation of 13. So this is the population of all women aged 18 to 24. They're going to have an average blood pressure of 115 and a standard deviation of 13. That is the information from the population about this. We're also assuming that the population is normally distributed, meaning if you just took a single woman, well, single in the sense that just an individual woman, and she's between the ages of 18 and 24, her average blood pressure should be 115 with a standard deviation of 13, meaning you can compute the probability that she has a blood pressure of over 130 or less than 100. since it's normally distributed, even though we only are going to have 23 women in a sample here, we're still going to be allowed to use z-scores and things like that. So if we take a sample of 23 women aged 18 to 24, find the probability that their average systolic blood pressure is below 110. So the mean of the sampling mean, which sounds weird, but the sampling mean, X bar, is normally distributed with a mean that's the same as the population. But its standard deviation is not going to be 13. It's going to be 13 divided by the square root of 23, because 23 is the sample size. So we can do square root of 23 divided into 13. That's what I'm doing right now. You're going to get about 2.71. So this is way different. For a single individual woman, her average blood pressure, the average blood pressure will be 115 with a standard deviation of 13. For a group of 23 women, the average blood pressure for their mean is 115. The standard deviation for their mean is 2.71. We're going to use this sample info if we're trying to draw inference about the average of that sample. And that's all there is to that one. I mean, we could draw the picture down there, but you know, it's not exactly necessary. You would just have a normal curve with an average of 115 and a standard deviation of 13. Here you'd have a normal curve with an average of 115 and a standard deviation of 2.71. So on the surface, it doesn't seem super interesting. I'd like to believe everything I say is super interesting, but I think most of you would maybe not agree with that. I don't know. Or you might say it because you kind of have to placate your professor a little bit. And if I go, you guys think I'm funny, right? You guys have to all go, yes, we think you're so funny. Yes, Mr. Hunter, you're totally funny, whatever. Yeah. But then secretly in your heart of hearts, you're like, nah, man, just quit deluding yourself is what you're saying in your mind. And you know what? That's okay. I'm only the slightest bit offended. Okay, my heart only hurts a little bit. Not too bad. Anyways, moving on from that kind of little weird thing. What was that? Was that the Twilight Zone? No, it was me pouring myself out there. No, I'm kidding. Suppose that so let's say you go to one of those oil change places, a 10-minute oil change joint, and they say, oh, well, we're going to get you an oil change in under 10 minutes. But in reality, they take about 11.4 minutes on average with a standard deviation of 3.2 minutes. Notice the big thing here, it doesn't say anything about being normally distributed. It's just that's the average amount of time they take. That's the standard deviation that it takes. So this could actually have a lot of funky different distributions. The bell curve is not the only distribution that exists in the world. There's all kinds of ways things can be distributed. But we don't know whether this one is normal or not. However, next up, we're going to take a random sample of 35 oil changes. We're going to take a random sample of 35, which goes beyond our threshold of 30. So even though the distribution that any individual oil change time comes from is not necessarily normal, it may be, but it's not guaranteed, the distribution of the sample mean is going to be normal because we have at least 30. So no matter what it asks, no matter what it asks, is X bar going to be normally distributed? Yes, because we have a sample of at least 30 and equals 30. That's what we need here. We either need to be told that it comes from a normal distribution or we need a large enough sample. If you get both, then it's certainly normally distributed. Now, mu of x bar, the average of the sample means, which sounds so weird to say, it does. It's going to be the same as the population average, which we said was 11.4. So bada bing, bada boom. That one, no computation necessary. However, the standard deviation that we need to concern ourselves with is going to be equal to the standard deviation of the population divided by the square root of the sample size. Thus, it's going to be 3.2 from above divided by the square root of 35. And so we go into our calculators. You can do 32 divided by the square root of 35 all in one breath. And you're going to get about, if we round to 2 decimal places, about 0.54. So the standard deviation of any one oil change time is 3.2 minutes. But if you take a 35 oil change times, average them all together, that standard deviation is only going to be 0.54, which we're about to see here is going to inform our decision making. So we're going to need to scroll down. Let's keep some of this information though. I'm going to need these 2 pieces of information. You too. 11.4 and 0.54 are going to be 2 pieces of information I'll need here in just a moment. I'm going to scroll on down. And my laptop just froze, I think. Oh, hey, you can do it. There we go. I might need to get a new laptop for Black Friday. Why is it freezing on me? Give me 1 second. Let me get this fixed. All of my problems are so small. Okay, I think that should take care of it. And I'm still recording. Very good. Okay, so back to this. We've already done that calculation. Now, we already argued that the mean was going to be 11.2, was it? And the standard deviation of interest was going to be 0.54. So if a random sample of n equals 30, oh, I'm sorry, 11.4 was the mean. Thank you. What's that? It'll make a mild difference, yeah. It'll make a mild difference. Thank you for that. But if you ever correct me again, I'll thank you. I'll thank you again for being diligent and really paying attention and focusing in. I have no qualms about being corrected because everybody makes mistakes. It's conceptual mistakes that you should worry about from your professor, not little memory or algebra mistakes. Okay, so anyways, we said that it had a mean of 11.4, standard deviation of 0.54. We're finally going to see all this brought together. For that random sample of 35 oil changes, what is the probability the mean oil change time will be more than 11 minutes? In other words, we want the probability that X bar, the mean oil change time of just those 35 things, not the mean of the population, but the mean of this sample of 35. We want to know what's the probability X bar will be greater than 11. Well, you may remember we had this cute little formula for z-scores because we need to go compute a z-score and then go look up a value on a z-table in order to do this. We had this cute little formula. Oh, you're so lovely. But this was for a single observation. A single observation X. But we're not talking about a single observation. We're talking about the average of 35 observations. So now the actual z-score formula we need to use, we need to modify it. We're going to call it X bar instead of just X. And then this sigma down here really is sigma over the square root of n. Because that is the standard deviation for a mean of 35 observations. So actually our z-score of interest here, z equals X bar is going to be 11. That's what we want to know. We want to know what's the probability that the mean of the sample will exceed 11 minutes. So we're going to use X bar there. Minus 11.4 all over, we already calculated that sigma over square root of n as 0.54. So we just got to do that calculation. We're going to get a negative number on top, which means the entire z-score is going to be negative. That's fine. Negative 0.4 divided by 0.54. You're going to get about, because remember, you got to round your z-score to only 2 decimal points because your z-table only has 2 decimal points. You're going to get a z-score of about 0.74. And we'll round it to 2 decimals. And so we've computed the z-score. We're not done because we want a probability. So we need the probability of a z-score, and this is already standardized, so I can just say z being greater than 0.74. And now we're squarely back in chapter 7 territory, where we need to go look up values from z-tables. Now you can use a z-table from your homework. Your homeworks will provide you with one. On the next exam, you really are going to want to make sure you have the formula sheet printed out or open somewhere, because that formula sheet not only comes with your chapters 7 and 8 formulas, it's going to come with a z-table. It's going to come with a z-table. So we need to look up the probability of a z-score exceeding 0.74. Well, I'll do it from my phone. So make sure you have a z-table busted out. You can Google one. You can just Google z-table. And I'm sorry, that's supposed to be negative. Oopsie. This is negative 0.74. Pardon. So we need to look up on a z-table negative 0.74. You'll get about 0.230. Let's use a different one. This one's bad. Me no like it. .2296. Okay, so this is a better z-table. But 0.2296 is the probability being less than it, so we need to do 1 minus 0.2296. And you're going to get, well, if you did 0.23, it'd be 7704. And that's our probability. So if I take a random sample of 35 oil changes, there's about a 77% chance that the average time among those 35 oil changes will be more than 11 minutes. I mean, that's unacceptable. The oil change place said it's a 10-minute job. If they just said it was a 15-minute job, I would walk away happy. I would be like, oh, they did great. So you just need to be careful what you claim. You need to back it up with some evidence and research. Just change. Nobody's going to be like upset that you're a 15-minute oil change place instead of a 10-minute, because all of us are just going to be watching TikToks on our phone or doing something on our phone or taking the opportunity to have a conversation with another human being and instead getting on our phone and doing stuff on our phone and looking at sports scores on our phones. But that's the bottom line. So they need to not claim they're a 10-minute oil change shop, because they just clearly are not. They have lied. Suppose a simple random sample of size 36 is obtained from a population with mu equals 74 and sigma equals 6. So mu and sigma given here are just the mean and standard deviation of the population that we're pulling a sample from. It does not say that the population is normally distributed. It doesn't say that. That's okay. That is okay. So let me uncomplete that. So sorry, the numbers changed very slightly here. So what we can see is that even though we don't know whether or not the population is normal, we are taking a significantly large sample size of size 36. And thus, it doesn't matter if the population's normal. What we can say is that the distribution of X bar, the distribution of the sample mean, is going to be approximately normal because we took a large enough sample size. You only take a sample size of size 8 and you don't know whether or not the population is normal, you have no idea what the distribution of X bar is going to look like. You don't. But large enough sample size protects us against that. So let's compute a few populations, or let's compute a few statistics about this. So suppose a simple random sample of size 36 is obtained. The original population has a mean of 72 and a standard deviation of 24. So let's find the mean and standard deviation of the sampling distribution of X bar. The means are going to be the same. Don't even have to think about it. The standard deviation is going to be sigma over the square root of n. So it's going to be 24 over the square root of 36. Because 36 is in the sample size. Well, that's nice because the square root of 36 comes out nice and clean as a whistle, and it just happens to be 6. Normally, the square root of a number doesn't come out. We did the square root of 35 earlier, and it gave us kind of a nasty number. You just can't help that, so you need to round. But this one, the numbers just happen to come out nice and clean, and we're going to get a standard deviation of X bar of 4. Yay. And we're not done with the problem, of course. We want to find the probability that X bar is greater than 76.6. Okay, well, we already have mu and sigma decided for X bar. We need to calculate a z-score first of all. 76.6 minus 72 all over 4. Which 76.6 minus 72 is going to be 4.6. and then we're dividing by 4. Maybe I can do that one in my head as 1.15. Oh, come on, don't bring that up. Hold on. Touch screens are a blessing and a curse. There we go. So we're going to get a z-score of 1.15. We want the probability then of a z-score being greater than 1.15. And I know it's greater because the original problem wanted it as greater. So what I need to do, I need to look up my standard normal distribution table, my z-score table. I need to go find 1.15, and I know it's a little awkward looking, but 1.15, 0.8749. Is that our answer though? No, this tells me the area to the left of it. So all I gotta do is take 1 minus this area, 1 minus 0.8749. And that's going to give you exactly 0.1251, assuming I did my mental math correctly. Hey. Okay, this next one, probability that x bar will be less than or equal to 62.4. Remember, when you're dealing with the normal distribution, less than or equal to, we're just going to pretend like it's the same as less than. In fact, it is exactly the same. We're not even pretending. But we just won't go into the theory about why. So let me erase all this. So now my z-score of interest is going to be computed. We're still going to subtract 72 and divide by 4, but the x bar is going to be 62.4 up here. Which may just change everything. That's going to give us a negative number. And then it's going to be 9.6. So it's negative 9.6 divided by 4, which is going to give you negative 2.4. If I'm wrong, let me know. But I believe that's going to be correct. So now we want the probability of a z-score being less than or equal to negative 2.4. Again, we can just pretend it's the same as z being less than negative 2.4. In other words, don't let the or equal to throw you off one bit. It doesn't matter in the normal distribution. So now I'm going to go to this table. I'm going to look up negative 2.40, and the probability is going to be 0.0082 down here. And I don't need to do the 1 minus thing because it already wanted the probability of a z-score being less than that. So it's going to be that. And it wants me to round to 4 decimal places, boom. And for this one, you're just going to have to compute 2 z-scores and find the probability in between them. So you might have to subtract one probability from another one. But basically, this is almost exactly the same as what we did in chapter 7, except we're throwing in the additional case that we have to take the standard deviation given and divide it by the square root of the sample size. But otherwise, it looks very similar, although conceptually, it's not the exact same. Conceptually, it's actually pretty heavy what we just added on today. But for practical purposes, your computations are only going to have a slight tweak over what we did in chapter 7 just last week, which is a little bit comforting. Okay. Moving right along here. We're rocking, we're rolling. We can work through this together here a little bit. So what we just did was we talked about the mean. We took samples and then we calculated the mean of those samples, the average value from it. But here we can talk about proportions. And so proportions work a little bit differently. A proportion is inherently one number divided by another. For our purposes, that proportion is always going to come out being between 0 and 1, including 0 and 1 themselves. So for instance, we just had what? A major presidential election happened this last week. It appears it has been decided, although there is, controversy and all that. But basically, we had a major presidential election last week. And in a given state, whoever captures the largest proportion of the votes in that state wins the electoral college votes for that state. So for instance, Pennsylvania has 20 electoral college votes. It appears that Joe Biden won Pennsylvania because he captured more votes than Trump did, but that's also the same as saying he captured a larger proportion of the votes cast than Trump did. So proportions here are going to be strictly between 0 and 1. In more general sense, you can have a proportion that is not. You can say 2 is your proportion or 2.5 or something like that, but not in this statistics course. So proportion is going to inherently be the number of successes divided by the total number of trials or things that have outcomed. So let's look at this. Let's talk about this population of numbers. We have the numbers 2, 5, 6, and 8. Within that population, what is the proportion of odd numbers? Well, there's only one odd number out of the 4. So the population proportion is going to be 1 divided by 4, which reduces to 0.25 as a decimal. This is the population of odd numbers this is the proportion of odd numbers in the population, aka the population proportion. We're looking back at the entire population. Now, this is a small population, but it is still a population. Well, what we're going to see here, so the population of odd numbers was 1 out of 4. The proportion ended up being 0.25. Now, what we can do here is we can take every sample of size 2 from this population of size 4. You can do 2 2s, 2 and a 5, 2 and a 6, 2 and an 8, 5 and a 2, 5 and a 5. You can compute all these proportions. The proportion of odd numbers in this sample, well, there aren't any. It's going to be 0. 0 out of 2. In this sample, you have 2 values, 2 and 5. 1 out of the 2 is odd, so you can have 0.5 is the proportion in that. This is called the sample proportion. It is our best estimate for the population proportion. So if you took a sample of size 2 and you got the numbers 2 and 5, you would guess that this came from a population that had a proportion of odd numbers of 0.5. That's your best guess. But what we know in reality is that it was only 0.25. So a sample of size 2 is not very good, even with your population being small. In this sample, the numbers 2 and 6, 0 out of the 2 are odd. In this sample, 0 out of the 2 are odd. Here, 1 out of the 2 is odd, so it's going to be 0.5. Here, they're both odd, so it's going to be 1. And in these samples, we're dividing by 2 each time. If you were to go down the line, what you would find is that the similar to what we just did, you would find that the average sample proportion is going to be exactly the same as the population proportion of 0.25. So if I kept looking at all kinds of different samples, the sample proportion is going to have an average value of 0.25, the same as the population it came from. The sample standard deviation is just going to be this really weird formula. It's going to be the population proportion times 1 minus the population proportion divided by the sample size, and then we take the square root of that whole crap right there, that whole business. How on God's green earth did we know it was this formula? In the last one, how did we know it was sigma over square root of n? That's a great question. It's because we didn't derive the math behind this from taking a little kind of example problem like we did here. The actual math and the numbers behind it were derived using actual math and statistical reasoning and analysis. So this is a key formula to remember. P times 1 minus P over N, and then the square root of that whole thing. The central limit theorem is going to tell us that as long as we take a large enough sample, and also one other criteria, we can assume that the sampling distribution is going to be about normal, roughly normal. So it turns out that we need a slightly different thing. So the 30 thing is usually how it is. But for this particular problem, we need n, the sample size, times p, the proportion from the population, times 1 minus p. We need that to be larger than about 10. That's a criteria that we need in order to say, oh, well, hey, we can use the normal distribution to do these computations. If you can't use the normal distribution to do your computations, you're kind of in a bad position. You're not in a good way there because you don't have a lot of other opportunities at you. If you don't have a normal distribution, how in the world do you calculate your probabilities? You have to go back to the drawing board and use some other statistical procedures, which may or may not be something that's in your wheelhouse at the moment. The mean, assuming we can do this, the mean is going to be P, the population proportion. The standard deviation is going to be this weird kind of pain in the butt computation, P times 1 minus P all over N, all of that inside of a square root. So depending on the source you're using, some sources say that this NP times 1 minus P needs to be greater than 10. You might see others say it just needs to be greater than 5. Let me check specifically because they always change it every semester. Let's check specifically what your homework is looking for. So we can be on the same page. Yeah, they want 10, okay. Which is normally the standard, but some homeworks like to do it different. So basically, earlier we had to check that the sample size was large enough that it was at least 30. Here, we can check that it's at least 30, and that's usually going to be sufficient. But we also need to check something else. We need to check that n times p times 1 minus p exceeds 10. That's going to be our checker this time. Okay, so let's go look at this example problem. According to the American Veterinary Medical Association, 37% of US households own a dog. I have a dog. He is a full breed bloodhound, and his name is Shepherd. and he's really cool, and I love my boy. He's a good boy. We tried to dress him up as Dumbo for Halloween because he has giant ears, and we were just going to let his own ears be like the Dumbo ears. He wore the costume for approximately 30 seconds and hated it, and ran around and immediately started whining, and so we had to take the dang thing off of him. But anyways, I'm just kind of digressing here. So according to the American Medical Association of Veterinary, whatever, 37% of U.S. households own a dog. So this means right off the bat, I have been given this information. The population proportion, we need to express it as a decimal, is 0.37. 0.37, 37% of U.S. households, we're going to say that's the entire population, have a dog. So we know that P is going to be 0.37. Then we go on and take a sample of 500 households. We determine whether or not they have a dog. So our sample size, N, is going to be 500, the number of things in the sample. So now what we can do is we need to check if it's normal shaped. Well, we need N times P times 1 minus P. We need that to exceed 10. In this problem, that's going to be equal to 500 times 0.37 times 1 minus 0.37. I'm going to use the calculator. Again, lean on the calculator when you are not strong. It will be your friend. It will surely help you carry on, for it won't be long. So it's going to need somebody to lean on in its own right. So we do this little computation. We get 116.55, which is far greater than 10. So, yeah, okay, we're good. We can use this little criterion. Yep, you get my stamp of approval. So basically, we can assume the sampling distribution of the sample proportion will be normal. It's going to be normal. It's going to be normal with a mean the same as the population mean of 0.37. I don't even have to think about that. 0.37 was the population average, or was the population proportion. So the mean of the sample proportions will be 0.37. That's what I'm going to use when I do normal distribution computations here shortly. And then I can use this square root of P times 1 minus P, or in business, that's going to be 0.37 times 1 minus 0.37. All of this inside a square root, all over 500. What you can do, I would do 1 minus 0.37 first. So I'm just going to give you my expertise here. 1 minus 0.37, which is going to be 0.63. I would do 0.37 times 0.63, which is 0.2331. I would then divide that by 500, which will give you a small number, 0.0004662. That's okay. Then take the square root of that business and round it. Let's just round to 3 decimal points. Let's round to 4 decimal points. Why not? Well, technically, according to operations, it is a little confusing. I would do the multiplication, the 0.37 times 0.63, because you're taking the square root of that entire thing, meaning you got to figure out what the entire thing reduces to first, then take the square root. Because if you do it first, it may only take the square root of 0.37, which is not what you want. So yeah, you do 0.37 times 0.63, then divide that by 500, then take the square root. And you get 0.0216. So the sampling proportion is going to be normally distributed, we already checked, with a mean of 0.37 and a standard deviation of 0.0216. We're going to use that to do normal calculations, normal probability computations here next time. We shall do that next time. And it's really just not so bad. It's not so bad. Okay, let me take attendance.